Right, now we're going to talk about uniform circular motion. Let's say you have an object that's making, it's moving, but it's moving at a circle. So you can actually draw it like this. So let's say you have an object that's moving, and you just form, keep moving in this circular motion, and it does not, go outside this circle. So in that case, what is the velocity associated with this kind of with an object that's moving that's forming a uniform circle? So because we say that it's uniform, it means that the velocity, the magnitude, or what we say speed, the magnitude of velocity does not change. But let's say, let me show a diagram first. So you have the object initially at this point, and it's making so the velocity at this point is tangent to the circle. So we have the velocity that's going that way. So this is the velocity, and this is the magnitude, and this is the direction of the velocity. And when it's moving, tracing out this circular motion at that top point, what is the direction of the velocity? If it's at this point, velocity is always tangent to the circle, and it's moving like that. So you have counterclockwise motion. So you have velocity that's at the top, still maintain the same magnitude, but now is actually pointing leftward. This is upward, leftward. What about here? At this point, tangent to the circle, draw a line that's tangent to the circle. So you can see that the velocity now is changing its direction and it's moving downward. At this point, it's moving rightward. What does that mean? It means that the speed. Remember, when you do that, the magnitude of velocity does not change. So the speed is a constant. It does not change. Speed is the magnitude of the velocity. What about direction? Upward, leftward, downward, rightward, and just keep moving like that, forming a circle. So we can see that the direction of velocity changes. So direction changes. And what it means is that when you have the magnitude, even though the magnitude is a constant, but then the directions keep changing, it means that there's a non-zero acceleration. So there's acceleration because the velocity changes. Remember, your acceleration is basically equal to the time rate of change of velocity with respect to time. At any given time, the directions of velocity is different. If it's different, it just means that there's non-zero acceleration. So the question is, what is the magnitude of that acceleration? So without going through the derivation, which you can look at in the lecture notes, there's the detailed steps that are there that you can find how to derive the acceleration for uniform circular motion. So let me just say that the acceleration what we found is that it has the acceleration. It's always pointing toward the center. Okay, so that's at this point, you have the acceleration that's pointing to a center. At this point, it's pointing to a center. At this point, pointing to the center. And this acceleration, we call that centripetal acceleration. Okay, so centripetal, because it's always center seeking. So centripetal acceleration. And later, in later chapters, you're going to learn that the acceleration is not just one acceleration. There's also another acceleration when it undergoes the rotational motion. But right now, we're just looking at the radial component that's directly along the radius. Okay, and so this is the expression for the acceleration is this. It's equal to the magnitude is v squared, velocity squared, and then times the radius. So the radius, this is the center, and this is the circle. So this is your radius r. So in that case, so this is the magnitude of the acceleration. What about the velocity then? How do we find the velocity? Now we know that that's within the time. That's within. What is it? So that's a period. What is a period? Period is the time that for the particle to make a complete circle, right? A one revolution. How much time is required? So your t. We use capital T to indicate that's a period. The amount of time that the object takes to complete one circular motion. So your t here would just be the distance traveled by the object divided by the velocity. We have the velocity v here. What is the distance then? Going from this point and then tracing out a circle, that would just be the circumference of the circle. So that would be 2 pi r. and then over the velocity. Okay, so in that case, you have the period that describe the the amount of time for the particles to make one complete circle, and you have the acceleration, which is v squared over r. You have the velocity, you have the radius, and how many revolution would would the object take? Then that would be just the inverse. So the amount of revolution for the object to take, that would just be inverse of the period. That just the how many revolution, or inverse of the time, and then you can find out how many revolution. Okay. So so that is that. That's it. So this is basically very simple, and we're going to revisit a uniform circular motion in other chapters later on. All right. So relative motion. So I just want to briefly mention about the relative motion in one dimension, and then extend it to higher dimensions. So imagine that you have an object that is in you can find the find the x and y. You can find, let's say, hold on. So say relative motion. So let's say we have two coordinate system. Okay, so let's say this is one. Let's say we call that frame A. And then you have another one, another coordinate system, and that's called that frame B. And there's a relative motion between them. So let's say it is, let's say this frame B is moving at a velocity. Okay, it's moving. So there's a relative velocity, between them. So frame B is moving at a velocity that's called that VBA. Okay, so in that case, so this is an object. So let's say you have an object. So you can definitely see that this is the locations of the object. In reference to, if you find the position vector expressed that in frame A, this would definitely be different from the position vector, when you use frame B, because frame B, they have a relative motion. Let's say this one is moving, is actually positioned at this point. So that's called that BA. Okay, so this is B and A. So this is the difference between them, and this is where the object is located. So in terms of A, in terms of A, you will say that this is X. We call that object P. So you have, this is a position, and this is the position of the object in front A. Okay, and in front A. And also there's a one that's also in frame B. So what we have here is that this object represented in frame A has to be equal to the object in frame B. This is object in frame B, so that will be this. And then plus the separation between these two. So plus XBA. Okay, so in other words, this object, when it's represented from, using the front A. In front A, this is, position XPA, okay, and it has to be equal to the position when it represented in frame B, and then plus the separation between frame A and frame B, okay. And so in that case, we associate the position of this object in frame A and frame B, and they are differed by this, the separation between the frame A and frame B. So if we look at this, we can actually take the time derivative of this to see how the velocity are in relation to each other. So let me write this again. So XPA is equal to SPB, and then plus XBA. And as you can see that this is PA. And when you have this, the B here, the subscript, they just like sandwich, so they just get canceled out. So you have XPA. So you have the first one and the last one that's consistent with this one. So let's say if we take the time derivative, because the time derivative will give us the velocity. We want to see how the velocity in relation to each other. Now that we know that how they relate in relation to each other in terms of the in the position vector. So you have dxba, and then dt. So this will give you velocity of the object in frame A, and this will give you the velocity of the object in frame B. Okay? What about this? This basically gives it, the relative motion between frame A and frame B. If frame B is moving at this velocity v, non-zero, then we call that v here. Okay? So you can see that if this frame A and frame B, they are moving, they are separated at a distance, and one frame is moving, is moving at a velocity from the other frame, then this is how the velocity measured in frame A in relation to the velocity measured in frame B. It's all about the measurement. Let's say when you want to measure the position of this one in frame A, you get xpb. I'm sorry, in frame B you get xpb. But if you measure it in frame A, you actually have the xpa. And how are they related to each other really depends on the separation between these two frame. Okay, and in terms of velocity, if you measure the velocity in frame B, we call that VPB, and also if you measure the velocity in frame A, we call it VPA. How are they associated with each other? And just by looking at this equation, we found that the velocity in frame A is equal to the velocity in frame B, and then plus the relative velocity between those two frames. Okay. Now, what about acceleration? So acceleration would just be another time derivative of this one. So whatever velocity measured in frame A, we take the time derivative of that, and we do the same thing for the velocity measured in frame B, and then plus dv dt. Now let's say if these two frames are moving away from each other, and this is so this velocity, if we assume that it is a constant, if it is a constant, which means that this goes away. If this goes away, and then this one gives you the acceleration measured in frame A. This is acceleration measured in frame B. But because there's no acceleration between frame A and frame B, so what we have here is that the acceleration in frame A is equal to the acceleration in frame B. Okay, so that's basically the characteristic when you have relative motion, and that is the position are related to each other by using this equation. So long as you know what is the separation between the two frames, and the velocity are associated with each other, differ by this velocity that's between the frames. Acceleration, there's no change. Whatever acceleration that you have in frame A is going to be measured at the same value in frame B, so long as these two frames are moving, at a constant they are separated by a constant, velocity. Okay, so that's basically that, and we're not even going to go over the two-dimensional, the relative motion in two dimensions, because so the same analogy applies to another dimension as well. You just have to use another, another vector to associate with the what happens in the second, dimension. Okay, so that concludes, chapter 4.